In this video, we will introduce the second part of the fundamental theorem of calculus. And typically moving forward, whenever we refer to the fundamental theorem of calculus, it's really going to be this property that we are referring to. So back in a previous video when we introduced the idea of enclosed area and the definition of the definite integral, I mentioned that at this point in time, it was not apparent at all why we were interested in talking about or thinking of this enclosed area problem. But now is where we're making the connection to this definite integral, i.e. some net difference of area, in this previous topic of antiderivatives. So we want to let little f be a continuous function and let big F be any antiderivative of the function little f. And remember what that means. That just means that big F prime is the function little f. So if you can come up with any antiderivative that you would like, this big F, then the value of the definite integral is going to be that antiderivative evaluated at the number b, the right-hand endpoint of the interval, and then we subtract away the function f evaluated at a, the left-hand endpoint of the interval. And some convenient notation is that oftentimes we will denote this as f of x, and then we put a vertical bar and we go from A to B. And this is just a fancy way of saying plug in B, put a minus sign, plug in A. And this fundamental theorem of calculus is going to give us a very quick and very convenient way to evaluate definite integrals. And I invite you to think back to how we used the definition and compare that to how much simpler these examples are going to become. So let's use the fundamental theorem of calculus to evaluate the given definite integrals. And let me just write this down to remind us. The definite integral from a to b of the function little f is big F of x, its antiderivative, evaluated from a to b. So what we need to do is think about, for the function given here, what is an antiderivative? Well, the antiderivative of 3x to the minus 4, well, our power n is minus 4 plus 1 is minus 3. So 3 over minus 3 times x to the minus 3. And we are going to think of that as being our function big F of x. That is an antiderivative of 3 over x to the 4. So by the first part of the fundamental theorem of calculus, we take that antiderivative, which is minus x to the minus 3, and we evaluate this from 1 to 5. So we plug in a 5, so that would be minus 1 over 5 cubed. We put a minus sign, and we plug in 1. Minus a minus is a positive, so we end up with 1. So this is 1 minus 1 over 125. 1 is 125 over 125, so this becomes 124 divided by 125. So let's look at the second example. What we need to do is come up with an antiderivative of the function x times the quantity 2 plus x to the 5th. So once again, I'm going to do just a little bit of work to the side. So that integrand simplifies, if that x is distributed, to 2x plus x to the 6. And the antiderivative, or in this case indefinite integral, is x squared plus 1/7 x to the 7th plus c. So an antiderivative, the part we need to worry about, the big F of x, is x squared plus 1/7 x to the 7th. So by the fundamental theorem of calculus, we get that function evaluated from 0 to 2. And remember, this is just a fancy way of saying we plug in 2. So in this case, that'd be 4 plus 1/7 times 2 to the 7th. We put a minus sign and we plug in 0. So 0 plus 1/7 times 0. So when we plug in 0, we get back 0. So the value of our definite integral is 4 plus 1/7 times 2 to the 7th. And keep in mind what these numbers are representing, some net difference of enclosed areas. But note that this method using the fundamental theorem of calculus is definitely much simpler than our previous approach that required us to use this definition, i.e. a limit of a Riemann sum. All right, so let's go ahead and look at a problem that would have certainly been, very, very difficult, actually impossible for us to evaluate before because we have this cosine x. Now we think, what is an antiderivative of cosine? Well, the derivative of sine is cosine. So because the derivative of sine is cosine, that means that the sine is the antiderivative. So it's going to play the role of big F of x. So by the fundamental theorem of calculus, we get this antiderivative, sine x, evaluated from pi over 6 to pi over 2. So we plug in pi over 2, put a minus sign, and we plug in pi over 6. And both of these values, pi over 2, pi over 6, are common values for sine. Sine pi over 2 is the number 1. Sine pi over 6 is the number 1/2. 1 minus 1/2 is 1/2. So one more example using the fundamental theorem of calculus. And now instead of doing the work off to the side, I'm going to go ahead and just do it directly underneath, which is going to be the typical approach. So first, let's kind of just pretend that the limits 0 to 1 are not there. Let's anti-differentiate term by term by just undoing that power rule. So x to the 4th, 4 plus 1 is 5. So this becomes 2/5 x to the 5th. Minus 3x squared. So 2 plus 1 is 3. So that would be minus 3 over 3, which is just a 1, x cubed, plus the antiderivative of a constant is just that constant x. And we evaluate from 0 to 1. When we plug in 1, we have 2/5 minus 1 plus 5. And then we subtract away what we get when we plug in 0. And if each x becomes a 0, we are simply left with a 0. So we have 2/5 plus 4. So 4 is 20/5, and this all combines to be 22/5.